So, welcome to this lecture on quantum physics and relativity. It is often claimed that quantum physics and relativity are hard to reconcile or even are incompatible. More optimistically, it has been claimed that both theories have a frail, peaceful coexistence. However, the effort and the interest for unifying them is increasing. In this lecture, I will try to show that quantum physics and relativity imply each other. You can't have one without the other. I do this by combining the results of two experiments. The first one is the experiment by Michelson-Morley performed in 1887 with the so-called Michelson-Morley interferometer, like the one sketched in this figure. The experiment established that there is no frame or medium that allows us to measure the velocity of light in an absolute way. Thereby, the Michelson-Morley experiment provided the observational basis for relativity. The second experiment is the one I proposed in 2010 to test the non-locality of the so-called quantum collapse of the wave function. That is, the standard quantum assumption that the decision of the outcome happens at detection. The experiment has been performed in Geneva, the University of Geneva, in 2012 by the group of applied physics of Nicolas Gisin. I will now discuss the Michelson-Morley experiment in the light of the experimental demonstration of non-locality at detection. Consider the setup sketch in this poster. A source emits pairs of photons, and one of the photons is used to herald the presence of the second photon in the interferometer. So, this photon is coming here and opens the coincident counter and heralds thereby that its twin photon is traveling the interferometer. So that is, we perform a Michelson-Morley experiment with single photons. We perform a single photon interference experiment. Once again, that is, in each run there is only one particle of light traveling the setup. The original Michelson-Morley experiment used white light with many photons at a time. Additionally, the original Michelson-Morley experiment used only one detector, this detector here, while here we will use two detectors. When the light enters the interferometer by this half-silver mirror or beam splitter, and it travels these two paths and meets these two mirrors and gets reflected. So, when light comes from this mirror reflected and arrives again here, light can take this path and reach the Alice detector A, or can take this path and by this circulator is guided to Bob's detector. So we will, in the same way for the light coming from this mirror, reflected from this mirror back, then it can take this way and be detected by Alice detector, or it can take this way and the circulator guides it to Bob's detector. Thereby, the Michelson-Morley setup is used in the experiment I am describing, is used to perform the basic experiment of quantum physics. That is, the interference of a single particle with itself. Suppose the photon would behave like a bullet that always travels a definite path. Then, light arriving here at this half-silver mirror or beam splitter, 50% of these little bullets would go transmitted and then come back, and 50% would go reflected to this mirror and then come back. So you have 50% going so, then back again, and in arriving here you will have 25% traveling to detector A and 25% traveling to detector B. And same way for the light traveling this path, for the bullets, if photons are bullets, traveling this path, they come back 25% reach the Alice detector, and 25% will reach Bob's detector. So you see that at the end you should have always 50% here and 50% here. So this would be the prediction if we assume light consists of many single particles. The experiment falsifies this prediction. If these two paths are equal in length, then you will get 100% of the photons here, 100% in Alice detector, and 0% in Bob's detector. And then, when Charlie changes the length of this path by moving his mobile mirror, then you observe this effect that the counting rate of Alice detector will decrease till 0%, and the counting rate of Bob's detector will increase till 100%. And then, if Charlie continues moving gently the mirror, then the counting rate of Alice detector will rise again, and the counting rate of Bob's detector will decrease again. You get so the characteristic sine curve of interference. Here you are in this axis you have the counting rate, and here in this axis you are plotting the phase of the phase of this interferometer. This means is a parameter giving the difference in the length of these two paths, the optical length and the difference of the optical length in these two paths. So you get these two sine curves. And this is the, what means this? This means that in order to get these patterns here, each detector has to be informed about the length difference of these two paths. So he has to be informed about the movements Charlie is, the settings Charlie is, the changes Charlie is doing here, each of both detectors. So the information about the length difference of these two paths arrives here and arrives here, more or less at the same time. But even if each detector reaches the information about the two paths, only one of them counts. If Alice's detector counts, Bob's detector doesn't count, and if Bob's detector counts, Alice's detector doesn't. For this reason, the decision of the quantum physics, standard quantum physics, assumes that the decision of the outcome happens at detection. The decision of which of these two detectors counts happens at the moment of detection. It doesn't happen at the beam splitter, otherwise you would get always 50% and 50%. So it happens at detection. This effect, the founding fathers of quantum mechanics gave to this effect the somewhat cryptic name of the collapse of the wave function. This collapse means nothing other that there is a coordination between these two detectors in order to establish an agreement that if one detector counts, the other doesn't count, and reciprocally. Historically, relativity arrived before quantum physics, but let us suppose that quantum physics had arrived before relativity. This could be very well have been the case. So we ignore relativity for a moment. Suppose you put these two detectors far away from each other. According to quantum mechanics, they will exhibit this coordinated behavior no matter how far away from each other they are. If we ignore relativity, this means that quantum physics actually assumes coordination between A and B, a coordination which works at infinite speed. But there is more. According to quantum physics, you cannot explain things in a causal way. You cannot say one detector decides first and the other adapts its decision to the first. Suppose you would like to explain things by means of causality in time, that is, assuming that the collapse happens infinitely fast, but nonetheless there is a time order. One detector decides first, say Alice detector decides first, and the other afterwards. Incidentally, David Bohm proposed a similar explanation, a similar time-ordered explanation with his non-local quantum potential. Well, then where can such a time order come from? Since the coordination works at infinite speed, the reason for such a time order, for such a supposed time order, can only be that the path from the beam splitter to detector A has not exactly the same length that the path from the beam splitter BS to Bob's detector. So, if we say, assume Alice detector comes first, this would mean that this path to Alice detector is a bit shorter than the other path to Bob's detector. And so, you could say that the information arrives before to Alice detector than to Bob's detector. And so, Alice detector would decide first to count or not to count, and thereafter Bob detector would adapt its behavior to the behavior of Alice detector. So you see, we are assuming here that it is always possible to define in an objective way which detector decides first. And this requires assuming that the speed of light is defined in an absolute way with relation to some medium or universal frame. And this was the assumption the original Michelson-Morley experiment tested. Suppose this assumption is true. Then you set the horizontal arm of the interferometer pointing in the direction of the orbital movement of the Earth around the Sun. So this path is moving in the direction of the orbital movement of the Earth around the Sun. Because of the movement of the Earth, the light will not travel these two paths, the horizontal one and the vertical one, will not travel these two paths in the same time. Actually, it will take a bit more time to travel the horizontal path and come back and then to the detector. So, consequently, the light will arrive from these two paths with a shift in the phase because of the time difference. Then it is like if light would be traveling two paths with different lengths. And so one should observe also a shift in the interference fringes. However, the original Michelson-Morley experiment demonstrates not shift at all. There is no shift in the interference pattern. It is the celebrated negative result of the Michelson-Morley experiment. To exclude that this result comes from a difference in the length of the two arms, from you say an error in the alignment, then the Michelson-Morley rotate the two paths of the interferometer this way. So, and by rotating the interferometer, then the orientations of the two arms are interchanged, and so you could exclude that the result was due to a difference, to a defective alignment of the interferometer. Well, now we accept that if we perform the experiment, the Michelson-Morley experiment, with single photons and two detectors, we get the same negative result. That is, no observable change in the counting rate of the detectors. Thereby, the Michelson-Morley experiment demonstrates not only that the speed of light cannot be defined in an absolute way, but also that the quantum collapse is not time-ordered, that the quantum collapse cannot be explained in terms of decision before and decision after, that is, in terms of cause and effect. In other words, the standard quantum idea of a decision and detection, which is not time-ordered, contains implicitly the principle of relativity and is demonstrated by the same experiment which demonstrates relativity. Unfortunately, Michelson-Morley experiment has not yet been performed with single photons and two detectors, like I am proposing here. And therefore, it is considered to be a relativistic experiment, and one overlooks that it is a fundamental quantum experiment as well. Well, from now on, we go on in the discussion taking account of all the relativistic knowledge derived from the Michelson-Morley experiment, and in particular the result that the velocity of light defines the very structure of the space-time, so that all interactions happening within the space-time cannot be faster than light. So now we take this for granted. All interactions happening within the space-time cannot propagate faster than light. And we consider now the experiment performed in Geneva in 2012. We use this simple setup. Light enters, impinges into this half-silvered mirror and can thereafter reach detectors, Alice's detector and Bob's detector. According to standard quantum physics, remember, the decision of the outcome happens at detection, not at the beam splitter. Otherwise, you cannot explain interferences. So it happens here at detection. When Einstein, in the 5th Solvay conference in Brussels in 1927, heard this explanation by the Copenhagen representatives like Bohr, Heisenberg, Born, when Einstein heard this explanation that the assumption of decision happens at detection, the explanation by the quantum collapse, he was upset and he said, this explanation, the decision, the collapse of the wave function involves an entirely peculiar mechanism of action at a distance, which implies to my mind Einstein said, a contradiction with the postulate of relativity. The experiment performed in Geneva in 2012 aimed to test Einstein's view versus the standard quantum explanation of decision at detection. The two detectors were set so far away from each other that they could not communicate with each other during the time of detection by means of any signal propagating in the space-time, that is, traveling at the velocity of light or less. Nonetheless, the coordination remained. Detectors I and B never counted together. So you have here the results. We set here if Alice detector counts, we put here 1, and then Bob detector doesn't count, is 0. If Alice detector doesn't count, 0, Bob's detector counts, 1. But the possibility that both detectors counts together never happened, or more precisely, joint counts of A and B were at the level of the noise. These are the results of the experiment. This experiment, you would get joint counts in two detectors if this coordination disappears. So the fact that you never have these joint counts in the two detectors proves that the non-local coordination between the two detectors remains independently of how far away from each other they are. The experiment in Geneva 2012 demonstrates what Einstein was afraid of, and that is quantum non-locality, which is already present in single particle experiments. You see, non-locality at detection is the very essence of quantum physics. It is, in fact, the fundamental quantum non-locality. Bell's non-locality, characterizing entanglement, is characteristic for two or more particle experiments, and Bell's non-locality derives from this fundamental non-locality at detection. Non-locality at detection is characterized the whole of quantum mechanics, all quantum experiments. It is really the essence of quantum physics. This implies that the quantum correlations between Alice and Bob's detector cannot be explained invoking a mechanism in space and time by any signal propagating at the velocity of light or less. And additionally, they are not time ordered. I have to say that I have worked and proposed experiments trying to explain this coordination by a time-ordered mechanism. This explanation fails. the predictions were refuted by experiment, and it is even worse if you accept that you can explain this coordination between the two detectors by a mechanism in space and time, then you would straightforward conflict with relativity. In other words, the Michelson-Morley experiment demonstrates the quantum non-locality. The quantum correlations, the Michelson-Morley experiment with single photons and two detectors, demonstrates that the quantum correlations come from outside the space-time. The time order independent quantum collapse, or the timeless quantum collapse, implies relativity. And relativity implies the non-locality of the quantum collapse. Quantum physics and relativity imply each other. You cannot have one without the other. And another important implication of the Geneva experiment is that the principles ruling the material world, like the conservation of energy, require non-local influences. Because if you accept that with one photon in the setup you can get here two photons, you are violating the conservation of energy. One photon, two counts. Certainly, you will have realms in which you get no count in each detector. So the energy would remain conserved in the average, but not in each single quantum event. So you see that to have conservation of energy in each quantum event, you have to have no local coordination between these two detectors. To conclude, quantum physics and relativity imply each other. You cannot have one without the other, and the principles ruling the material world, like the conservation of energy, require non-local influences. Thank you very much, and thank you also for your patience with my English.